Welcome to the Contractors Institute. My name's Richard Elsey, and I'll be going over this construction mathematics for you this morning. So sit back, relax, and enjoy. Okay, maybe there's a couple of things you did not know or you forgot over the years. Okay, so let's look at some of this. Construction math, common math used in the construction industry. So I did a course on the basic mathematics, which you should have watched before watching this. But if you haven't, this is just going to go more in depth with the math that we use here in the construction industry. One of the things that we're always using to lay out, well, at least most contractors are. Now, there's some contractors don't know what I'm talking about, but most of us use this. It's right triangle leg lengths, Pythagorean theorem. You know, it's Pythagorean may not have been a real person, what they tell me, and it's real depressing, but, you know, we'll get through it. So we just need to know the formulas for this. Now, sometime in my history, long time ago, I had a teacher stand up in front and say, all right, you need to learn this today. A squared, B squared, C squared. A squared plus B squared equals C squared. And at first I looked at it and thought, I can do this. A plus B is C. Even I'm smart enough to figure this out. But I didn't. I wasn't. I didn't pay attention. And, of course, I'm looking at it and it's just all looking Greek to me. So, well, let me just skip it. I get down to shop. Now, when I was going to school, my shop teacher was the disciplinarian of the school. So if you couldn't keep up or you acted up, you had to go to shop. So I spent a lot of time with my shop teacher. He was a nice man, maybe, but tough guy. Anyway, get down there, and we were building little playhouses. We had to build them, and then they would sell them in front of the school. Then they would put the money back in the proceeds of the other things in the school, geek club and all that. So whatever it's called. So we were back here building playhouses. Well, of course, he comes over and he says, Rich, you got to make that floor system square. If it's not laid in square, when you set your walls and you got to put your roof on, nothing's going to line up for you. So that's part of it's real important to you. And I said, well, okay, how do I do that? He said, well, right triangle leg lengths. Remember we were taught that? No, sir, that's the reason I'm here. And he said, okay, Rich, let me teach you the construction way, the hard-headed, method. He said, come here. He said, give me your dumb end of the tape. And I handed him the dumb end, and he walked out a distance, and he stopped, and he measured that, at 3 feet. Then he called me. He said, come here. He said, now you walk out this way and measure a distance 4 feet out. And I did. He said, now, Rich, measure from this mark here to this mark down here. If it measures anything other than 5 feet, you're not laid in at a 90-degree angle. You're not square. Okay. And that work? Yeah, it's a shortcut. Okay, so he said, look, here's the formula. A squared plus B squared is C squared. So A squared plus B squared. Then we're going to hit square root key. So one of them's A, one of them's B. It doesn't matter which one you want to label A and which one you want to label B. 3 squared. Okay, let me do this. Plus 4 squared. I'll do the mathematics for you. 3 times 3 is 9. Plus 4 times 4, which is 16. And then 9 plus 16 is 25. That's C squared. Now remember, all we have to do is hit the square root counter calculator and unsquare 25. And that's going to tell me that's 5 feet. So a 3, 4, 5 is simply a shortcut to right triangle leg lengths. And it was like, oh boy, I halfway understood it, enough that I went back and was bragging to my math teacher that I understood it, but I still didn't understand why if 4, 5, 3, 4, 5 works, why won't 6, 7, 8 work, And finally, she sat down with me, the math teacher, and said, Rich, you're saying the formula right, but you're not thinking it correctly. What's the formula? And I said, well, you just told me it was a squared plus b squared is c squared. She said, that's right. So it's not a plus b equals c. It's a squared plus b squared equals c squared. Oh, okay. And then she drew this out for me. She says, you understand the 3, 4, 5, right? Halfway? Yes, ma'am. And she said, well, look at it like this. If I took those numbers and squared them on the outside of the triangle, and then when she did that, I immediately understood it. I said, oh my gosh, I never thought about it like that. Area A is 3 by 3. Area B would be 4 by 4, and area C is 5 by 5. So 3 times 3 is 9, 4 times 4 is 16, and 5 by 5 is 25. Now if I look at it, area A plus area B equals area C. A squared plus B squared is C squared. Then C squared minus B squared is A squared. 25 minus 16 does equal 9. Then C squared minus A squared is B squared. 25 minus 9 does equal 16. So there's all the numbers right there. Now unsquare each one of these numbers to get one side of the square. The square root of 9 is 3. Okay, the square root of 16 is 4. And I push 5 on my calculator and the square root key. That's 5 feet. There's my 3, 4, 5 triangles again. So a 3, 4, 5 triangle is simply shortcuts to right triangle leg lengths. A squared, B squared equals C squared. Okay, so hopefully they're not as hard for, what everyone seems to want to make them. Okay. Now, of course, if 3, 4, 5 works, then you're going to see these. If you need larger numbers, use multiples of 3, 4, 5. 6, 8, 10, 9, 12, 15, 12, 16, 20, 30, 40, 50. They all work. So the bigger you go, the bigger the numbers you can use, the more accurate it's going to be. Okay. Right triangle leg length. So if you can remember the 3, 4, 5, you can remember A squared plus B squared is C squared. Hopefully. Now here's a question, just put in there to see if everyone could do it. To verify the building for layout for square before excavating for the wall footings, a contractor sets up batter boards 3'6" outside the four corners of the building. The strings intersect on the outer face of the 8-inch by 8-inch by 16-inch concrete masonry units. What is the diagonal distance from the string intersections at the northeast and southwest corner? Shoot. Now, keep in mind on the, whenever we look at this, we look at a plan set. Now, I'm not going to open up my plan set right here on the computer for you. But there's what it is. Now, I always go, the top of the page is north, the bottom of the page is south, and then spell we, W-E. So they're talking about this northeast corner up here, northeast, and southwest corner down here. So I need this diagonal measurement. Now it told me I set up my batter boards 3'6" outside the four corners of the building. Okay, set them 6'6" outside the four corners of the building. That's nothing to do with the question. The question was asking me, what is the diagonal measurement from the string intersections, which are on the outer face of the 8 by 8 by 16-inch concrete wall, okay, the block wall. So I set my batter boards, pulled the strings, and I want this measurement right there. Now, one of them is, one dimension is 63 feet, and the other one's 53 feet. So one of them's A, one of them's B. Whatever one you want to label A, label it. Whatever one you want B, put it down. It doesn't matter. The hypotenuse or side C of the triangle is what we're looking for. So A is 63 feet. B is 53 feet. So C is the square root of A squared plus B squared. 63 squared plus 53 squared. Now 63 times 63 is 3,969. 53 squared is 53 times 53, which is 2,809. Add those two together, 6,778. That's c squared. Now remember, push the number or the square root key on your calculator. What number times itself is 6,778? And unsquare the number, one side of the square. And that'll tell you that that comes out to be 82.33 feet. 82.33 feet. 82 foot, 4 inches. 0.33 is 4 inches. Okay. So that was the answer to it. Now the next thing I want to look at is estimating volume of the void. This is about an elevator pit that's shown to us there on the screen. How many cubic yards of concrete are required to pour the elevator pit? Now, it's one of those things I have to admit to. Not so many years ago, we always did this as I would calculate the 4 walls, and then I would calculate the base slab, and then I would add everything together to come up with the correct answer. Yeah, that's one way to do it. But as we were in class one day, a lady comes up, she says, "Rich, look at this." She says, "I did it a different way and it seems to work." She goes, "I know it's 9'4" by 9'4" on the outside dimensions. And if you look at the outside depth, it's 5'6" plus a one thick base slab down there, 12 inch. That would give me 6'6". And then I have a 6 inch slab up here. That's 7 foot. So if I took 9.33 by 9.33, 4 inches divided by 12 is 0.33. Multiply that by 7 foot deep, that's cubic feet, divided by 27, that would give me enough concrete to pour the whole thing solid. And that's what I told her. And she said, "Yeah, but I didn't pour. I did another calculation of this area." She says, "I knew the void right there was 8 by 8, took 7 foot and backed out the 12 inch base slab. That's 6 foot. Divide that by 27, and I'm done." She just subtract that from the total. So she was doing it like this. Solving it as a solid pour, and then deducting what's missing. I said, wow, we never thought about it like that. But yeah, that works every single time. And it's probably more accurate because I don't have to worry about the walls being a different thickness. Every wall could be a different one. Wouldn't bother me. So yeah, that's a lot quicker. So we're going to take the 9'4" by 9'4", 9.33 by 7 foot deep, divide that by 27, and that's what tells me that if I would pour this solid, I would need 22.56 cubic yards of concrete. Well, I'm not going to pour it solid, at least not today. Maybe another day, but today I'm going to deduct it. Now remember, because of the 8 inch walls, it's an 8 foot by 8 foot, length times width, but the inside dimension is only 6 foot because of the 1 foot thick base slab. Divide that by 27, and that's 14.22 cubic yards. What's left over is 8.34 cubic yards. That's the 4 walls and the base slab all at once. Okay. 8.34 cubic yards. So it's a lot quicker than, 4 walls and a base slab and then add them all together. That's, a lot of chances of making a mistake. Every time I write a number, it's a chance of making a mistake. So the least the better. So this is quicker. Okay. Well, to follow through with it then, if this were a tank, just a water tank, how many gallons would be in the tank? Just pause for a moment, see if you're punching in the numbers on your calculator yourself, and I'm sure you are. But we just said, well, Rich, it's an 8 foot by 8 foot. It's a square. It's 6 foot deep on the inside. That'll bring us right to the top of the wall. Okay. But that's 384 cubic feet. Now, let's know how many gallons of water is in there. Well, I know a gallon of water is 8.34 pounds the weight, and I know a cubic foot, a 1 foot by 1 foot by 1 foot box, that will hold 7.5 or 7.48 gallons of water. So if I took 384 cubic feet and multiplied that by the 7.48, the number of gallons per cubic foot, that'll tell me my tank is going to hold 2,872 gallons of water. If it were a tank. Okay, just wanted to use that 7.48 there. So that's what it's used for. Every cubic foot, there is 7.48 gallons of water that will fit in there. 7.48. Well, here's another exciting one for you. This is like it's your birthday. If there are 112.5 concrete block per 100 square foot of wall area, the total number of 8-inch stretcher blocks required to construct the pool equipment room is blank. Deduct for the door openings. Include the bond beam block. Okay. Okay. So, an 8-inch by 8-inch by 16-inch block, or a 7 5/8 by 7 5/8 by 15 5/8. Close enough. Add a 3/8 of an inch mortar joint to it, and you're back up to an 8 by 8 by 16. So, an 8 by 16-inch block, if you think about it, is 8-inch by 16-inch nominal dimensions. That's 128 square inches, length times width. Well, if I take a square foot, 144 square inches, 12 inches by 12 inches, divide that into the 128, the area of a block, that will tell me that I need 1.125 block per square foot. So every square feet of area I need 1.15 square feet. That makes sense. Area of a block. So here's the equipment room here. Now all it wants me to do is calculate the number of block that I need around this to construct it. And it did tell me to minus this door down here, 3068 door, okay, opening. And it gives me the dimensions here. I know this is 20 foot 8 inches. This is a 12 foot 8 inches. It would be 20 foot 8 inches down here, and it would be 12 foot 8 inches over here. So I know the linear dimensions of my walls. Back out the door opening, 3068. That's easy enough. So 20 foot 8 plus 12 foot 8 plus 20 foot 8 plus 12 foot 8, so on. Now I know the height of the room. I had to go to the typical wall section in order to see that in a plan set. But at the typical wall section, I saw it. Okay. Now it tells me that the wall height in this equipment room is 7 foot 4 inches. Now, before everyone gets started, well, you can't build that at 7.4. No, you can't. And I'll admit that. But listen, guys, these plans, when we drew them and put mistakes in them so that when we were teaching the building inspectors and plans examiners, that we could use the prints, the same set of plans. So that's why we put mistakes in them. So if you caught it, that's great. If not, you can't build 7 foot 4. So, but that's for our purpose. That's the height of it right there for our purpose. So I'm going to add all these up and subtract out the door, and it's 3068 doors. So it's a 3 foot by 6 foot 8 door. So do the math. 20 foot 8 plus 12 foot 8 plus 20 foot 8 plus 12 foot 8. It's a 66 feet 8 inches all the way around. Okay, all the way around. Multiply that by the 7 foot 4. That's 488.69 square feet of area, square footage. Well, we know we got to deduct for the door opening. So back out that 3068 door, that's 20.01 square feet. So I need blocks, enough blocks for 468.68 square foot of area. We also said that we need 1.15 block per square foot. So 468.68 multiplied by 1.125, that's going to give me my answer and let me know that I need 528 block there, 528 of them. All right, now here's the formula for equal spacing. Now we use this, gosh, think about it. You know, studs, trusses, rebar, light fixtures, fence post. I mean, if more you think about it, you could sit here and name more and more that we space on equal spacing. Now the formula that we do that for is length in feet divided by spacing in feet plus 1. Now the 1 is for the starter, the first one. Now some people look at it and call it the end course. Well, if you call it the end course, you know to add 1, so you're good to go. So length in feet divided by spacing in feet plus 1. So the question I have is, studs are spaced 24 inches on center of the wall, measuring 100 feet in length. The number of studs is how many? Well, it's 100 feet in length. Divide that by the spacing in feet. Now, if you took 24 inches divided by 12, that's 2 feet. I know y'all know that. So 100 feet divided by 2 feet, that's 50 foot, or 50 of them. Add 1 in for the starter, add 1, 51. That would tell me that I need 51 studs to do the job. Okay. Another question says, if floor joists are spaced 16 inches on center for a deck measuring 48 feet 8 inches in length, the number of floor joists required would be how many? It says make no allowance for the double end joist. So just take a second. 48 feet 8 inches. 8 inches divided by 12 is 0.67 feet. And I'm going to space them every 16 inches apart. And I don't need to worry about my double end joist. It tells me that as part of the question. So 16 inches, divide that by 12. That's 1.33 feet, 1 foot 4 inches, 16 inches. So 48.67 feet in length. Divide that by every 16 inches, or 1.33 feet, and add 1 in for the starter, okay, because I can't do it with 0.59 of a joist. It's a whole joist or no joist. So we always round up there, always round up. I need 38 joists in order to do this, 38. Always round up. All right, here we have drop, run, and grade. Trade knowledge. They don't put this in too many of our books, but I found this in an old plumbing book. Okay, and I'll show you here. Not this. I mean, this is just drop, run, and grade. It's what it is. I mean, whenever you talk about run's always going to have a horizontal to it. Now, think about a drop or a rise. If you're at the top of the hill looking down, it's a drop. But if I'm at the bottom of the hill looking up, it's a rise. So you call it a drop or rise, same thing. It's vertical measurement. And whenever we talk about a grade, grade's always going to have a slope to it. So run is always horizontal. Drop or rise are vertical, same thing. And grade always has a slope. There you go. I impressed you now. It's like, daggone, I'm so glad I know this. Okay, I didn't know what it was, but geez. But, all right, here's a sign of drop running grade, downright good. Now, put this formula in here, found in an old plumbing book. And what you do is you cover up what you're looking for. You know, so if I put my thumb over this, I have numbers above and below each other. Well, when they're above and below each other, it means division. So this is the drop divided by the run. Well, drop divided by the run equals a grade. So that formula works. Now, if I cover up the run, it tells me to take the drop and again and divide it by the grade. Drop divided by the grade does equal the run. That works. And, of course, if I want to know what the drop is, let me put my thumb right over that. Now I have two numbers side by side. Whenever I have two numbers side by side, it means to multiply. So run times the grade equals the drop. There's all the formulas right there. Drop divided by the run equals a grade. Drop divided by the grade equals a run. And run times grade equals a drop. So all of them work there. Now, the one thing you have to remember is when this comes out, if this is 0.0, say 36, I want to convert that to a percentage. So they taught me in school I can either multiply this by 100, and that would tell me that that's 3.6%. Or I could have just took the decimal point here, like I was taught, and do a quick conversion and just move it 2 places to the right, 1, 2, and add a percent sign. 3.6%, same thing. So you could do it either way. Just understand how to convert a decimal to a percentage. Then, of course, we need to remember how to convert a decimal or a percent back to a decimal. So if I have 8%, well, I can divide it by 100. And that'll tell me that that's 0.08, okay? Or I could simply move the decimal point. Again, this is 8.nothing%. There's nothing here, but it is a decimal point. If I move it 2 places to my left, 1, 2, and drop the percent sign, that's 0.08, same thing. So what it ends up being is, either way you want to do it, it works. Now, this formula will always help. I mean, it's easy to remember. Even if you're out in the field working, you could pick up a 2x4, draw a circle, and cut it in half horizontally, then bottom section in half vertically, and write in DRG, downright good, drop, run, grade. And then just cover up what you're looking for. So even in the field, this will end up helping us quite a bit. Okay. All right, this question says, refer to the parking lot on sheet C01. The asphalt parking lot has a straight line rise of 6 inches from the center line of catch basin 1 to the north curb line. The percent grade of the asphalt is blank. All right, well, let me look at this. Here it is. Now notice this is the curb and gutter. It comes off Joliet Street all the way around the parking lot back out. Here's catch basin number 1 over here. Now it told me from center line of this catch basin north to the curb line up here we're going to have a 6-inch grade. 6 inches divided by 12 or 0.5 feet, either way. So it's 6-inch drop, and which is a good thing. I mean, that's going to force water to drain toward those catch basins right where we want to put it. So draw up my circle here. Let me cut it in half horizontally, drop running grade. I'm looking for the grade. So it says take the drop, which is 0.5 feet, divide that by the run in feet. So the run, what's the measurement from there? As I come in off of Joliet Street, I see this curb right here in the parking lot, and it shows me it's 20 foot. From outside of this curb to the outside of this curb is 20 feet. Then I look over here and it tells me Joliet Street is 28 foot wide. Half of 28 would be 14 feet from either side. So 20 plus 14 is 34 feet. So if I can take and do the math here, the drop of 0.5 feet divided by the round of 34 feet, it tells me my grade is 0.014. Now either multiply that by 100 or move the decimal point like I did, and it comes up to be 1.4 or 1.5% if you round it up. So either answer would be correct, 1.4, or you could call it 1.5%. All right. Now we're getting ready to work on this, but I had to show you the steps before the questions. So what we're doing here, we were going to build a set of steps. And we were going to, here's the print, but the architect stepped up and gave us a change order. Now the architect tells me, instead of putting in a set of steps right here, because someone in the household is handicapped, he wants us to put in a ramp here. A ramp. Now, we're trying to figure out how far is this ramp going to extend out. He knows that the ramp only needs to have an 8% grade to it. Well, from what he already gave me, I know the height of this set of steps is 21 inches. 7 plus 7 plus 7. 7 plus 7 plus 7 is 21 inches. Now, some of you, okay, Rich, let's put it in feet. Divided by 12, and it's 1.75 feet. 1 foot, 9 inches. Either way. So in a drop of 1.75 feet, we have a grade of 8%. Well, again, what am I looking for? DRG. I'm looking for the run. I know the drop is 1.75 feet. Divide by that by the grade, tells me right here the grade is 8%, or that's 0.08 in decimal form. And that would give me the run. How far out are my steps going to extend? Okay, and here's where it comes in. The architect has specified a concrete ramp with an 8% grade in lieu of the wood deck shown on sheet A03. The formwork should extend out blank feet from the face of the deck. All right, well, that's the question I just answered. We have a 21-inch rise and an 8% grade. So drop divided by the grade. Drop is 1.75 feet. Divide that by the grade of 0.08, and that's 21.87 feet. So our ramp, that's what it's going to extend out, 21.87 feet. Mathematically, if you converted this number and get used to converting the numbers, 0.87, times 12, and then that'll give you 10 whole inches, but part of another inch. multiply that by 16, and we end up with 7/16 of an inch there. So 21 feet, 10 and 7/16 of an inch. Now this is just a visual. Little foundation down there. That little square is the pile cap. Little dots are the pilings. And that line you see coming off of them, that's the grade beam. So here comes the wood pilings down. We drove those into the ground. Then on top of those, we embedded, okay, those pilings up into our pile cap. So we formed it up, okay. A lot of you thought that was a concrete, but of course you can't put the concrete down until you have the form up. And we have to put some reinforcement steel in it. Okay, there's our mat of reinforcement steel. Now we can place the concrete. Okay. And also we're going to add a couple of anchor bolts into our concrete. Now, this is a grid point, just simply where they meet. Here comes the base plate. Okay. Now this connects the column. And that shows us it's a W8 by 60. Now the W tells me the shape of the beam. It's a wide flange steel beam. An I-beam would just simply be smaller. It weighs 60 pounds per linear foot. So it's a wide flange steel beam. It's 18 inches in web depth and it's 60 pounds per linear foot. Okay? That's what all that means. Then our grade beams connect them together. There's looking at the lot, all the pilings driven in the ground all over the lot for us. Last I checked, they were, what, $1,200 a pile? $1,200, $1,400, something like that, to get them driven. Well, that's marine piles, so that's not land piles. So there's our anchor boats. There's our guys putting them on. There's a base plate. Case connecting everything together. They got their hard hats on in case that boat would fly up and hit them in the head. I mean, that's important. Here's what I was trying to get to, our column and pile cap schedule. Now notice these, B2, B3, C2, and C3. Now those were the columns in the center of the building. Okay, B2, C3, C2, C3. Now let me look at this. Here it is. This is a wide flange steel beam. It's 8 inches in web depth. And here's the weight. It weighs 60 pounds per linear foot. Well, I know I got 4 of them. I know the weight is 60 pounds per foot, but what is the length of that column right there? Well, if I go to the top, it says top of the column is 25.50 feet. Top of the column. But I have to look here. Here it says finished floor is at 0.00. From finished floor to the top of the pile cap is another negative 3.5 feet below that. And if I'm at the top of the pile cap and I'm visualizing this, I'm at the bottom of the column. So it is 29 foot each. So refer to sheet A06 and A11 on the plan set. The total weight of W8 by 60 steel columns placed on pile caps at grid points B2, B3, C2, and C3 is how many tons? Well, how many steel columns do you have again? 4. What's the length of each column? 29 foot. Okay. The column weighs how much? 60 pounds per linear foot. And the part of trade knowledge for you is how many pounds are in a ton? 2,000. Okay, hopefully most of you knew that. A little bit of trade knowledge. Trade knowledge is, knowledge that you already know that they don't bother to put in the books for us. Okay, we know this. We don't need to, a no book. So, 4 columns at 29 foot each, 116 feet. Well, the weight is 60 pounds per foot. That's 6,960 pounds. And it's asking me how many tons is that? Divided by 2,000. And we found out we have 3.48 tons. Now, keep in mind, it is answer C up there. But if I would have only calculated 1 column in the building, 0.87 tons. If I would have missed the 3.5 foot section below finished floor, 3.06. If I would have calculated all the columns in the building, 13.92. So no matter how you might make a mistake, the answer's there. So always be careful when you're working. All right, the next thing we're going to look at then is a board foot calculation, which typically board feet shouldn't be that hard for us. A board foot is simply a 1 inch by 1 inch by 1 inch thick board. A 12 inch by 12 inch by 1 inch thick. 1 foot by 1 foot by 1 inch. So whenever I'm calculating a deck, I know every square foot of deck using nominal dimensions that's 1 inch thick, it's 1 board foot. So I have a board foot for every square foot of area on 1 inch thick deck. Now, if it's a 2 inch thick deck, I have 2 board foot per square foot. Starting to confuse people. All right, now here's what's happening. My spouse is a customer from hell. They call you out, want you to give them an estimate on this deck for they're wanting to build. Now, she tells you to build half of the deck out of 1x6s. And the other half of the deck, she tells me to use 1x8s. For aesthetic purposes, to make it look a lot prettier. Looking at it, you should be able to tell. So, and she says, Rich, in the backyard, she goes, just in the middle of the yard, I want a deck with 200 square feet of area on it. Okay. And again, I stopped asking why years ago. It's just, okay, let me just, have it done or do it myself. And all right, so let me order board feet. I'm going to have to order this deck out of board feet. Never done that before, but all of a sudden I wake up and I feel, gosh, I'm just going to make everyone happy, and I'm going to call up the material supplier and tell them I want my deck and board feet. So since she told me she wanted 1x material, and it's 200 square feet of area, and I'm going to use nominal dimensions whenever I calculate board feet. So every square foot of deck is 200 square feet there. That's 1 inch thick. Use nominal dimensions, so it's really 1 inch thick. That's 1 board foot per square foot. So if I have 200 square feet, I have 200 board feet. Okay. All I have to do is take the square feet of the deck and multiply that by the thickness of the board, however thick the board is. If she comes out now and looks at me and says, Rich, look at you. 1x material's never going to hold you. We better get 2x. Do they sell 3x? No, 2x material now. So she tells me to get, 2x6s and 2x8s and build a deck now. So now how many board feet do I need? Well, square footage of the deck, 200, multiplied by the thickness of the board, 2 inches thick. That's going to give me 400 board feet. And if it's 3 inches thick, that's 300 board feet. And so on. All right. So anytime you have a question about a deck, you simply take the square footage of the deck and multiply it by the thickness of the board. So now look, if it's not anything other than a board, we take the thickness in inches times the width in inches times the length in feet divided by 12 gives me board feet. It's like, yeah, Rich, but you keep, now you're telling me I'm mixing feet and inches. I mean, that's one of the things we said not to do is mix feet and inches. We're not. It's the poorly written mathematical formula is what it's doing. This is the way it's written in a book for reasons I don't know. But look, if I take the length in feet here, let me take that out of the equation. Length in feet. I want to multiply that by the width in feet. Well, here it's giving me the width in inches. Well, in order to convert width into feet, I'm going to take this width and divide it by 12. So it cancels these two out. Now multiply that by the thickness of the board, and that's board feet. So that's the same thing as the deck. Length in feet times width in feet is square feet. We're multiplying it by the thickness of the board, and we're done. Board feet is a quantity of wood found in lumber, and that's what we're trying to calculate here. Okay. So decks are easy. The square feet times the thickness. So if it's 1 inch, 1 board foot, 2 inch, 2 board feet. So the 2x each required to plank a 12-foot by 24-foot deck is how much? Well, 12 by 24 is 288 square feet, I believe. Multiply that by 2 inches, and that's 576 board feet. Square feet times the thickness of the board. So actually, board feet is going to be one of the easier things you do. It's simply, we never order anything by board feet. Maybe hardwoods. So if you ever go and you want to build your deck out of oak or cherry or, any of the hardwoods, then you could order by board feet. Other than that, keep ordering by the square feet. So the way you do, you call up and order board feet, and they ain't going to know what the heck to send you. Okay. Sounds good on paper, though. Now, here's what I was talking about. If it's not a deck, how many board feet of wood are found in 2 inch by 12 inch pine joist that is 14 feet long? Well, it's in use nominal dimensions again. It's a true 2 inches by 12 inches. And I have 14 feet of this. So 2 inches by 12 inches by 14 foot long divided by 12, and that'll tell me I have 28 board feet. So it's the thickness in inches times the width in inches times the length in feet divided by 12 is board feet. So now you know what I'm talking about or what anyone else is talking about when they talk about board foot. Okay, board feet. Quantity of wood in lumber. Calculate the board feet in 6 1 inch by 8 inch by 8 foot cedar boards. Well, there's 6 of them times the thickness in inches, 1 inch, times the width in inches of 8 inches, times the length in feet divided by 12, and I have 32 board feet. Centerline estimating. Remember, centerline estimating is simply average estimating. That's all it is. Average. Right down the middle. Now, I don't want this to confuse you, but it says, why do we estimate its center line? And it says, refer to the diagram of the 8-inch block wall corners, okay, when viewed from above. Now, look at the first one. If I try to use, when I'm doing a calculation, inside dimensions, I will miss my corners when I calculate them. So I don't want to do that. The second picture shows me that, well, if I use outside dimensions, I'm going to overlap the corners. I'm always going to overlap them. I don't want to do that. It's the centerline method. Okay, if I go right down the center, see the area that I overlapped would be the same area that would fit out here. So it's going to average out. So I want to use centerline estimating whenever I do my estimating. Okay, centerline estimating. And again, it's average. See, this is just average right down the middle. Okay, same thing I just said. We overlap. Like Goldilocks. Just right. Okay. So inside corners cancel outside corners. All right, now think about this, guys. This has how many 90-degree turns in it? 4. Has to. Think about it. Start here. Somewhere here, from here to here, I made a complete 90-degree turn. Okay, here I started out heading west. Here I'm heading south. Now I'm heading south, but all of a sudden somewhere within here, I did 90 degrees. Now I'm heading east. Now I'm heading east. Now I'm heading north. Another 90-degree turn right here, from here to here. And another 90, okay, from here to here. I turned 90. Now I'm heading west again. Now, keep in mind, trim carpenters and other framers, you may understand this. Every time you have an inside corner will cancel out an outside corner. An inside 90 cancels an outside 90 whenever you're thinking about this. So anything we do is only going to have 4 90-degree turns on it, even a circular shape, 4 90s. So every inside cancels an outside. So if I look at this, okay, that's corner number 1. Inside cancels outside. There's another inside corner, cancels an outside corner. There's corner number 2, second 90-degree turn. Inside will cancel the outside. There's third one, inside cancels outside. Inside cancels outside. There's a fourth. So an inside corner will cancel out an outside corner. So there can only be 4 90-degree corners whenever we're doing this, 4 90-degree turns. Okay. So if you have inside dimensions, add the number of corners times the thickness of the work when viewed from above. So if I did this, okay, the thickness is 2 inches all the way around that perimeter right there. That's what it's trying to show me. I would simply, if you have outside dimensions, subtract the number of outside corners times the thickness of the work when viewed from above. So if I add up these dimensions all the way around, that's 260 linear feet. 70 plus 60 plus 40 plus 40 plus 30 plus 20 is 260 feet. That's outside dimensions. If I want to know what these centerline dimensions are, I need to subtract the number of outside corners, there's 4 of them, 4 90s, times the thickness, which is 2 foot thick. That's the width of it. Now, 4 times 2 is 8. 260 minus 8. The centerline dimension is 252. okay, from the center line. Now here it says if the inside dimension sums is 252, now it's telling us the inside dimension in here. This is 252. Then the center line length would be what? Now notice now, because we have inside and we're going to center line, we're going to add, that's why we did here, 4 times the thickness. Again, it's 2 foot. 4 times 2 is 8. 252 plus 8 is 260 again. So if you're given outside dimensions, you subtract the number of outside corners times the thickness. And if you're given inside dimensions, you add the number of outside corners times the thickness. So either way, you come up with centerline estimating, or once again, it's all average estimating. Average. You're just going right down the middle. Now, using the builder's level is the next thing. There's the abbreviations. Benchmark, back sight, height of the instrument, foresight rod rating, station elevation, and the formula for that. Then you have the formulas: benchmark equals back sight equals height of your instrument, minus the foresight rod rating is the station elevation, or benchmark plus the back sight equals height of the instrument, minus the station elevation equals the foresight rod rating. Now, this is a rod. Typically, they're given in tenths. This is a builder's level. Notice it's locked down and it's level. Now, the one that we can move up or down is called a transit level. You can move it up at a 45-degree angle. And then surveyors use one called a theodolite. It rotates, or simply a transit. It goes 360 degrees vertically and horizontally. But the poor old builder's level here, it only rotates horizontally now. Okay, horizontally. Will not go up or down vertically. Now here's what it is, and all I'm going to do is show you this graphic. If I'm standing here at my instrument, once I set it up and make sure it's level, if I look back to a known reference point, that's called the back sight rod rating. Now remember, it's the vertical measurement from here to here. So all I'm doing is adding the benchmark plus the back sight equals the height of the instrument. Now the height of your instrument minus your foresight rod rating would give you a station elevation. Because remember, this is down here again, but the foresight rod rating is the vertical height right here. Okay, that's the vertical height. So let's look at these formulas and see if they don't make sense to us. All right, now what this question is going to ask, it says refer to sheet C01. A contractor wants to verify the grade elevation at the top of the retention pond. An instrument was set up in a mulch area number 1 and a rod reading of 5.40 feet was obtained from the Joliet Street benchmark. Now a 5.90 foot reading was then obtained from the top of the retention pond. The grade elevation is what? Now there's something here that's not missing, and the reason it says to go to plan C01 is so that we can get our benchmark elevation. Now our benchmark on a plan is given to us at 98 feet. I'm just going to give you that. So if I set up my builder's level and it's level, okay, it's got a bubble on it. I look over at Joliet Street. Now in the middle of Joliet Street on a plan, if you had it, it would say 98 feet. Now, 98 feet is the elevation of Joliet Street. The benchmark that it gave me at 5.40 feet, that's the vertical measurement between here and here. So if I start at 98 feet, then I go up 5.40 feet, that means this elevation now, okay, is going to be 103.40 feet. All I did was add benchmark plus the back sight equaled the height of the instrument. Then I took the height of the instrument and subtracted out the foresight rad reading. So I turned my builder's level. Now I'm looking at the station. Now the station is given to me out there. And they said when I was looking forward, okay, so I did turn my instrument. Now I'm looking toward the station. I took a reading of 5.90 feet. So that's the vertical measurement from here to here. If I want to know what my station's elevation is down here, I need to take the height of my instrument and subtract this vertical measurement out, which is 5.90 feet. And that would give me the station elevation there of 97.5 feet. So if you think about it, all I did was go up, over, and down. I add it and I subtract it in that order. Now, you might be able to look at these and say, well, look, to me, just looking at it, it looks like the benchmark or the station's going to be 6 inches lower than the benchmark. Because standing at this point, if I look this way at 5.40, this way at 5.90, that's 6 inches lower. I am. Joliet's 98 feet. My station's 97.5 feet. I'm 6 inches below the benchmark. Now this, let me explain this. If you looked at C01, and I may put it in here right after this, on C01 it shows us finished floor, first floor is 100.00. That's when we were in civil series. But when we switched to architectural series, it switched to 0.00. So civil series, it is 100.00. Architectural, it's 00. That's where we reset the scale. Now, it shows me here on this typical wall section, to get to the top of the pile cap here, this is the pile cap, I have to go 3'6" below first floor elevation. Okay. That's negative 3'6" inches. Now, if I go 3'6" below 100.00, well, 100.00 minus 3'6", 3.5 feet, 96.5 feet. So, if I placed a target right on top of that, this would be at 96.5 feet. Okay, so it leads me into this is what it is. It says refer to sheet C01 and A09. A contractor is setting up pile cap forms. An instrument was set up in the pull area, and a rod rating of 5.40 feet was obtained from the Joliet Street benchmark. A rod was then set on top of the pile cap form. The correct rod rating should be blank. Now, remember what I said, if you go to C01 of the plan set, that's where you're going to see the site plan. And you'll see finished floor elevation is 0.00. But when you turn to the foundation plan in the architectural series, you start seeing it at 0.00. So that was just for me to explain that it's the same elevation. Two different ratings, one's civil, one's architectural, but same elevation. So a contractor setting up pile cap forms. An instrument was set up in the pull area and a rod rating of 5.40 feet was obtained from the Joliet Street benchmark. Now the rod was then set on top of the pile cap form. The correct rod rating should be what? Well, it starts out the same as we did before. We would go to the plan set, which it told us to, and from there we can get our benchmark rating again. It's 98 feet. The bike site rad rating once again is 5.40 feet, so that has not changed. So that's 5.40 feet. So then the height of my instrument then is 103.40 feet. Well, here's what it is. When I turn to look to my station, that's where I said that on the top of the pile cap form is at elevation 96.5 feet. That's where we took the 100.00 and backed out to 3.5 feet. Now, I want to know what this distance is. That's what I'm looking for now. Well, I know from here to here, this is at 103.40 feet. Down here is at 96.5 feet. So what's the difference between these? 103.40, subtract out 96.5, and that would tell me the foresight rod rating there is 6.90 feet. That's the foresight rod rating. So once again, we add and subtract. Okay.